Welcome everybody. We would like to present the observationally constrained multi-scale dynamic rupture modeling study of the 2019 Ridgecrest earthquakes. We use the physics-based dynamic rupture framework to understand the 2019 Ridgecrest sequence. The first constraint is the geometry of the model. We construct a complex 3D fault network following the method from Sara Carena that basically integrating geology and geodetic and seismic data. The second is initial stresses. We found dynamics of both events show very high sensitivity to the 3D stress state, specifically in the vicinity of complexity of fault geometry. We find that it's important to account for regional tectonic 3D stress setup, plus the long and the short-term stress transfer that has been accumulating in the region. The second ingredient that also mentioned before is pre-Ridgecrest Coulomb failure stress change to the previous major earthquakes. So this is building on work of Alessandro Verdecchia. We are adding some positive field stress, additionally loading the source region. We are running both earthquakes in same models. The 7.1, we will see all the static and dynamic stress changes that 6.4 produced, and we are accounting for off-fault plasticity. So we are having a proxy of off-fault material yield at the stress exceeding simple Drucker-Parker plasticity criterion. The third is the fault strength. We are taking into account rate and state friction with rapid velocity weakening. We are assuming a simple depth dependent of A and B parameters, and we are scaling the seismogenic depth by the seismicity. The fault strength is described as a relative pre-stress ratio called the R ratio. These are key factors. Two of them can be observationally constrained, and another two can be constrained by few calculations. First is inertial stress. The SX max is from the SCEC community model, and we are assuming the Anderson and stress state plus the additional Coulomb stress changes. The second is stress shape ratio, and the third and the fourth parameter where we perform calculation are the fault strengths of optimal oriented fault, and the fluid pressure found it to be elevated but still below hydrostatic. We use supercomputing, but not a lot of it. We need around 8 hours on 64 nodes of SuperMOOC-ng, and our model is resolving up to 2 Hz wave propagations on 200-meter fault geometrical sampling. Our model shows 2 conjugate faults ruptured simultaneously, but only one segment that actually breaks the surface. Here are some snapshots at 2, 4, and 6 seconds, and we can see that hypocenter is very close to the intersection. Magnitude fits nicely, and average rupture velocity around 2.5 km per second, and we have 1.5 to 2 meter maximum slips. This is a summary of model validation plot. We can see that the accumulated slip, a comparison to the kinematic source model performed by Frantisek Gallovic using Bayesian inversion approach. We have the back projection using aftershocks calibrated method performed by Bolli, and we can nicely see that 2 faults being activated. We can compare the moment rate. We can see nicely 2 peaks corresponding to both of the faults. We also calculate synthetic fault surface offset and compare with the INSAR data. We also have a good agreement in terms of surface deformations compared to INSAR, GPS, and strong ground motion data, especially given that this is not inversion. So here we show comparison to the static GPS, continuous GPS data, and strong ground velocity. A bandpass filter is applied and amplitude is scaled. The 6.4 event causes a static Coulomb stress of about 0.25 megapascal at the hypocenter location of the 7.1 event. Here we find the maximum shear stress that is carried by waves during the 6.4 event, which is around 0.8 megapascal. This is not enough to dynamically trigger the 7.1 event. Our 7.1 models show complex ruptures, including reactivation of the 6.4 conjugate fault. And an interesting feature is that the earthquake tunnel beneath geometrical complexity. Magnitude is nicely fitting, and maximum slip is 3.8 meter. The rupture begins as a crack and later on turns into pulse-like rupture. We also capture the dynamic of southern segment that's now they are both activated. We can see the final slip of 7.1 even and compare with the kinematic inversion. We can compare moment rate, the fault surface offset, and back projection result. One important fact that our average rupture speed is 2.5 km per second, faster than most published kinematic models ranging from 1 to 2 km per second. We think that we are missing the fault zone that would be slowing down rupture here. However, we still have a good agreement compared with the static GPS, continuous GPS, and ground velocity. We can see a slight azimuth-dependent offset, which is caused by rupture speed and directivity effect. Our result gives us a proxy of fault zone width by looking at the accumulated plastic strain. This is plotted here in comparison with damage proxy map. We can see that in the region where we have increase of fault plasticity is also increasing the dynamic barrier behavior of geometric complexity. In summary, we perform the combined dynamic rupture scenario of Ridgecrest sequence, which can be constrained and validated by the observations. We show high sensitivity to the 3D stress state, specifically in the vicinity of geometric complexity. We see 2 conjugate fault ruptures simultaneously in the 6.4, and 7.1 re-ruptures the conjugate fault. The 6.4 induced Coulomb stress and dynamic shear stress in 7.1 hypocentral region. However, not enough to dynamically trigger it, but both scenarios match key observations. We also see a good match with seismic and geodetic data, given this is not inversion study. However, we might be missing the near fault zone that's capable to slow down the rupture speed. In more general context, the physics-based modeling provides mechanically viable insight into the key factors that govern rupture nucleation and interaction in a complex fault system, and helps constraining competing views on earthquake sources. Observational constraint can now really be included and also can help constrain observational methods themselves.